This is the first in a series of videos about clustering, and we're going to start by talking about mixture models, which is actually a fairly general form of clustering, but I wanted to try to give you the full picture first, and then we'll look at specific types of different mixture models and variants that are, I guess, more narrow in scope. So the outline of this video is going to start with an intuition or an intuitive discussion about clustering and what it is. Then I'll explain mixture models, which is one strategy for formalizing the goals of clustering. And then we'll look at one specific instance of a mixture model called the mixture of Gaussians, or a Gaussian mixture model, which is probably the most famous form of mixture model. And then we'll look at the expectation maximization algorithm and see how that can be used to learn the parameters of a Gaussian mixture model, and specifically how it gets around some of the computational and statistical challenges that come with a mixture model or trying to learn the parameters of a mixture model. Okay, so clustering is an unsupervised learning task, and the goal in clustering is that you get a bunch of data examples and you want to organize your data examples into clusters or into groups of examples that are similar in some way. And you can draw the type of input you might get for clustering in 2 dimensions, as I've done on the screen. And if you're looking at this on a small enough screen, you can probably see what the clusters should be. You can kind of guess that there's 3 groups of points, and it gets even clearer if we add more points that also represent these clusters. So you can see that there's a cluster on the left, cluster on the right, and one on the bottom. And again, the task is unsupervised, and then the way that the task is defined is so wide open that there's lots and lots of variants of what you might want to, how you might define what is a good clustering. And this is kind of the nature of unsupervised learning, is that the task tends to be less well defined than it is when you're doing supervised learning, because our goal in unsupervised learning is to look at data and learn something from it. So how you define that something really has a strong effect on what is considered a successful unsupervised learning. So there's lots of variants. And in some cases, you might be interested in doing hard cluster assignments. So that's a situation where we look at each point and we say exactly which cluster does it belong to. So if there's 3 clusters, we say, does this point belong to cluster 1, cluster 2, or cluster 3? Or we might have instead a distribution-based assignment, where you might be allowed to have a point that's right in the middle and say that it's reasonably evenly split among the different clusters, or with some probability it's in each cluster. And then there's other variants like hierarchical clustering and lots of other things, but we're going to spend most of our time, at least for the immediate future, on distribution-based clustering, which you can reason through it. It actually generalizes hard cluster assignment, right? You can imagine that if we are allowed to assign a distribution to each data point, we could also easily just assign delta distributions, where there are all the probabilities on one particular cluster, which gives us hard cluster assignment. So what sort of distribution can we use to describe a cluster or a clustering like this? The answer, or one answer, is a mixture model, where we have data that comes in, and this is just some initial notation. So the data comes in the form of a bunch of examples. So there's n examples, and a mixture model then talks about the probability of each example. So it's gonna have a product of all the probabilities of each example, and for each example, it's gonna take the expectation. So it's going to sum over all possible classes, all possible clusters. So Ci is going to range from 1 to k of the probability if it were part of that cluster. So there's 2 pieces to this probability here, or this expectation. The rightmost piece is the probability of the xi, of the observations of the ith example, if I is in cluster Ci. And then on the left is the probability that example I is in cluster Ci. So when you do this sum of all the possible cluster assignments, we get the expected probability of xi coming from any cluster. So this probability distribution, this mixture model distribution should suggest a generative process. So based on this, the way that we've weighted the expectations, here's how we would generate data to match this probability value. We would, number one, we would first sample which cluster each data point should come from. So we sample from P of C or P of Ci. And once we've picked a P of Ci with the appropriate probability, then we also sample, or then we use that Ci to sample the data example. So we sample from P of Xi given Ci. And the reason this is called a mixture model is because it's a mixture of lots of different P of X given C's. So P of X given C's can be a bunch, there's a K of them, capital K, total different P of Xi's given C's, and they're all mixed together with the ratios given by P of C. So let's make this a little bit more concrete, and we'll talk about the Gaussian mixture model. So in this situation, we have exactly the same thing I wrote on the previous page, except now we've parameterized P of X given C, and we've parameterized P of C, but that was pretty much decided just based on the notion of these being distinct clusters. So P of C is a multinomial, which means you roll a die to decide which cluster you're in. And then once you decide which cluster you're in, you look up the Gaussian parameters. So you look up a mean for that particular cluster and a covariance matrix for that particular cluster, and then you sample from the Gaussian. And this is a conditional Gaussian because the mean and covariance parameters depend on the C, depend on the class that you're in. To visualize this, we can look at an example I drew up in MATLAB. So there's a bunch of Gaussians on the screen, and I've circled them in red. It's probably hard to see, but you can see these Gaussian clouds, right? These clouds that look like each of them by themselves looks like a Gaussian, but now we have lots of them and they're mixed together, and there's different ratios of them, right? The bottom one appears to have more points, so we might assume that, I actually don't remember what the values were that I generated this from, but we might assume that or we might infer that the probability of that particular cluster is higher than the others. And one fairly obvious point you can make from you can get from this picture is that by allowing a mixture of Gaussians, we can capture much more exotic shapes of point distributions than you would be able to with just a simple Gaussian or a single Gaussian. Right? A single Gaussian could never get this configuration of wide points and skinny areas and L-shaped connections. Right? It would just be like an oval, bell curve shape. So another thing that you might notice is that the clouds can overlap. So there's no, it's not necessarily going to be looking for clusters that are separate from each other. It's more just looking for different pieces that seem to be generated from different parts of a distribution. So this goes a little bit counter to what people typically think of when they think of clustering, but this is also clustering. I mean, we basically, even though there's a smooth transition between two overlapping Gaussian clouds, the fact that we believe that each of the points should be generated from a Gaussian tells us that this is actually two distinct normal distributions creating this data. And another point you might notice is that we wrote the equation so that it was indexing from C equals 1 to K, but if you look at these pictures, there's no identity for the clusters, right? I could have numbered them, as I've shown here in green, right? It could be numbered 1 through 5 this way, or it could be numbered 1 through 5 this way, and mathematically they should be equivalent because that summation, it doesn't really matter which one is attributed to cluster 1 versus cluster 2 versus cluster 3, as long as all the clusters show up. So this idea of there not being an identity, a numerical or an indexed identity for the clusters, reveals something about the any goal we might have for fitting a distribution or distributional parameters to data. what it reveals is that there's a non-convexity in the negative log likelihood, but in really any objective function, or most objective functions you might use to decide how good your Gaussian parameters are. So if you think about convexity, one of the ways of thinking about convexity is thinking about the behavior of a function that you're wondering about whether it's convex, the behavior of that function as you interpolate between 2 points. So you might have 2 points on the left and on the right, and a convex function is gonna dip down underneath those 2 points, or in the extreme case, it will stay flat in between those 2 points, or it could be dip down even further. I mean, the idea is that it cannot go above the points in the middle, otherwise it's got a concave region. So if we have a convex, if our hope is that we have a convex learning objective, a convex objective function that rates the quality of a parameter setting for a Gaussian mixture model, then on one point we might have a configuration A, B with the Gaussian means and covariances visualized here, and in another point we might have B, A, and these are completely equivalent, right? There's no reason for A or B to be considered special in any way, that you can't just swap the two identities and get the same distribution. So this is solution 1 and this is solution 2, and if we had a convex objective function, or if the negative log likelihood was convex, then that would mean that a point in the middle would get us, a better solution. It would give us a better scoring solution. Or if things are flat around this region, it would give us a no worse solution, right? The solution cannot be worse than either of the 2 endpoints. But if we think about, fitting a bunch of Gaussians to a point, this was very unlikely to occur, or it's very non-intuitive for this to occur, because a point that would be in between these 2 solutions would be one where the two Gaussian clouds are much closer together, and it would be very strange to have data for which this is a better or no worse solution, or this is the better or no worse solution than the ones that are the solution 1 and solution 2, which have separation. Or more accurately, this could happen if the middle solutions were actually better fits for the data. But if you imagine that the solution 1 and solution 2 were really good fits, you wouldn't expect that then moving those points closer, moving those clouds closer, would give you a better fit. So this is a kind of hand-wavy cartoon example of why we know, or how we can think about knowing that the negative log likelihood for a Gaussian mixture model is non-convex. And of course you can do the math out and show that it isn't convex, but it's useful to have this intuition. But now that we know that it's not convex, how do we handle this? So the strategy that is the standard way for training these types of models is the expectation maximization algorithm. And I'll just go over here, how you do EM, expectation maximization, or EM, for Gaussian mixture models. And in the next video and in class, we'll go over more details about the general idea. What I'm showing you here is just the specific form for the Gaussian mixture model. So we get as input a bunch of examples, and they're not labeled because this is unsupervised, so they're just points. They just have features. There's no labels, it's just features. And our goal is to learn Gaussian mixture model parameters, so that's going to include the multinomial probability, or the multinomial distribution for all of the cluster memberships. So this is just going to be k probability values that sum to 1. We'll have the mean for every single class. So there's going to be k different means, each with dimensionality d, and k different covariance matrices, which have dimensionality d by d, right? And this is going to be for C from 1 to k. And as part of the training process, we're also going to be considering latent variables. So these are going to be variables that represent which cluster did each data point come from. So there's a zi that's going to take a value from 1 to k. For every data point I, we're going to have a variable that tells us which cluster it came from. Now, of course, we never see these variables. We never know what the values of these variables are, which is why they're latent. And to robustly reason about these latent variables, we will have latent variable probabilities, so P of z. So this will be of a similar form to P of c. It's just a multinomial probability distribution, but it will be different for every point, or it can be different for every single data point. So the P of c is really a prior probability. It's a prior probability. It's the general probability that everybody uses for sampling a data point. And then P of z is the notation's a little bit, I'm abusing the notation a little bit. Really P of z is going to be P of z given all the evidence that we have, right? So given what we see, what we know about mu, the mu and the sigma, mean and covariance, what we know about x, based on those, what is the probability that each I is in any cluster? And of course, these are multinomials, so they must sum to 1. Okay, so those are the pieces, and the outputs are the Gaussian mixture model parameters, and the latent variables are going to be things we're going to use during the learning process. And you can, the general procedure is you initialize the Gaussian mixture model parameters to something, and then you repeat the expectation maximization process, which has 2 phases. It has something called the E step, or the expectation step, where we fit the latent variable probabilities. So we basically say, using the current values of the Gaussian mixture model parameters, what is the maximum likelihood setting of the latent variable probabilities? And if you do the math, you get this. And you can think about this for a little while and see how the equation, or this update equation, corresponds with fitting the probability of each point being in any class, given the information that we have. Right, so the numerator there is the likelihood of the data coming from this class, or it's the joint likelihood of the class being C and the data coming from the Gaussian for class C. And then the denominator is the likelihood of the data, because it sums over all the possible classes. So therefore, what you're left with is just the probability of which class the point I is in, conditioned on the Gaussian parameters and the observations. And then the second step, or the second phase, the M step, which is the maximization step, is where we fit the Gaussian mixture model parameters using the expected likelihood. So the update equations are as follows. So we update the prior cluster membership probability by just taking the average P of z. We take the average probability, latent variable probability. We fit the Gaussian mean for each class by taking the weighted average of the points weighted by their cluster membership. And lastly, we fit the covariance in the same way. We weight the difference from the mean by the cluster membership probability. And this is the recipe. And there's a lot more to understand here, but this is an instantiation of the expectation maximization concept, which is a much more general idea for any latent variable learning scenario. And we'll do some more analysis of expectation maximization, but what you should be aware of is that what it does under the hood, or partially under the hood, is that it takes the non-convex, or rather non-concave likelihood function, or log likelihood function of the Gaussian mixture model, it finds a lower bound, a convex lower bound for it, and then optimizes that lower bound. So this is the strategy, and the picture, you can draw it out like this. So imagine that the curvy line that I've drawn, let's say that's the log likelihood of the data given the parameters, and this is what we really want to maximize. We want to find the maximum likelihood, or we want to minimize the negative of this function. And the way we do it is we start with an initial guess. So we initialize, I don't know, we'll talk about initialization later, but just some arbitrary initialization. And we fit this lower bound to the objective function. And this lower bound actually turns out to be the expected log likelihood using a very simple distribution. So rather than using the true distribution for z, we use a simple one that factorizes easily, which is just like what we showed on the previous slide, where we were just independently sampling z from p of z. So once we have this lower bound, we can then optimize it exactly, because it's it has a closed form solution, which is the m step, and we have a new point. Then we then use that new point to find a new lower bound that's even better than the previous one, and then optimize that exactly. And then we keep doing this until we hope that we land in some local optimum. Now, of course, this is a very optimistic picture I drew, because a lot of times, something else can happen, which is that you start with some initial point and you come up with a lower bound, and here's another lower bound, which is not as nice looking as the one I showed you before, but this could be what's happening in higher dimensions. And you optimize that, and then you optimize again, and you end up with a solution that's a slightly worse solution. And there's not too much you can do about this. I mean, this is a non-convex or non-concave optimization, and the best thing we can do with a polynomial time algorithm or with a reasonable running time algorithm is guarantee a local optimum. So because of that, it's important then to think about what does the log likelihood really look like for EM, or for a mixture of Gaussians. And again, this is all cartoons, but you can imagine that it looks something like this, where you have a likelihood function with a bunch of equally good global maxima. So these are the best possible fits of those Gaussians, and they all look exactly the same, but maybe they just swap the identity of different Gaussian, different C values. And then you also have a bunch of equally bad local maxima. So these are maybe just fits that get stuck, that you can't find a better solution from. And they're all equally bad because they're isomorphic in that you can just swap the identity of the clusters and get the same solution. And then there's also bad local minima, which can occasionally cause problems depending on what algorithm you use. And it's actually an open question to me whether expectation maximization can suffer from this problem. There was a very interesting paper that came out at NIPS last year about this, where a lot of local optimization methods for non-convex learning objectives, people generally think of the main problem with non-convex optimization as worrying about getting stuck in bad local optima, or if you're trying to minimize local minima, or if you're trying to maximize local maxima. But what they were arguing was that you actually get stuck in other zero gradient points, which are these minima, or the optima in the wrong direction, which can also have zero gradient, and therefore may not tell you how to get out of those situations. So it's possible that EM can get stuck in these too. Possible in the sense that I don't know whether it's impossible, but it's something to be aware of, that there can be these degenerate solutions. So one of the important things to help avoid getting stuck in bad local maxima or local minima, if those are possible, is good initialization. So in an obvious statement, if you start at really close to the true optimum, the global optimum, then you're gonna do well. So some heuristics that work pretty well in practice for initializing these things are, one, just use completely random and maybe try a few restarts, rerun the algorithm a few times just to make sure you don't get anything better. Or another idea that people like is to fit a single Gaussian to all of the data. So you get parameters that are roughly in the right ballpark. You'll have properly accounted for skew in the data. So if one dimension is very wide and the other is very narrow, then fitting a single Gaussian will capture that. And then you randomly perturb k copies of them so that each of them is slightly different from the other. Another idea is to randomly initialize cluster memberships and then just start with an M step instead of starting with an E step. So what you do is you randomly assign cluster memberships and then you fit Gaussians to all those cluster memberships, which will roughly give you the same effect as the second point of fitting a single Gaussian to all data, but is, to me, I think is a perhaps more principled way to randomly perturb. Right now you're perturbing by subsampling the data. But there's lots of, these are just heuristics. There's few guarantees here. We're working with non-convex optimization, so there's not that much you can guarantee about what happens. But these work pretty well in practice, and there's lots of other strategies too. Okay, so next time we're going to talk about variational expectation maximization. So the more general form, the more general idea behind expectation maximization, and that will lead to an interesting variant of Gaussian mixture models, which uses hard EM, which is an extreme variant of expectation maximization, that leads to the k-means algorithm. And I've intentionally done it this way, where I'm showing you the full mixture model training algorithm, and then I'm going to show you k-means, whereas other people would probably show you k-means first because it's very intuitive. But I want to show you that k-means is a special case of the general expectation maximization procedure.